The light entering your eyes right now is 8 minutes old. Not metaphorically old, not approximately old, exactly 8 minutes old, give or take 20 seconds, depending on where Earth currently sits in its elliptical orbit. The photons striking your retinas as you read this left the surface of the sun when you were doing something else entirely, when you had no awareness that these particular particles of light existed, when they had not yet crossed the void between your star and your planet. They traveled 150 million kilometers through space at 299,792 kilometers per second and arrived at your eyes carrying information about what the sun's surface looked like at the precise moment of their departure. You are not seeing the sun as it is. You are seeing the sun as it was. You are always seeing the sun as it was. Every photon that has ever entered your eye from the sun arrived carrying a delayed message from the past, a snapshot of conditions that no longer exist by the time the image forms in your visual cortex. This is strange enough on its own, but here is what should genuinely unsettle you about it. The delay is not a technical limitation of your visual system, or a consequence of the speed of your neurons, or a property of the atmosphere through which the light passed. The delay is baked into the structure of reality itself. It is a consequence of the fact that light travels at a finite speed, and that the universe does not permit information to travel faster than that speed, regardless of what technology you bring to bear on the problem. You will never see the sun as it currently is. No one ever has. No one ever will. The most advanced civilization imaginable, equipped with instruments of unlimited precision, looking at the sun from Earth's surface, would still be looking at the sun as it was 8 minutes ago. The delay is not removable. It is fundamental, and this is only the beginning, because the sun is close. 8 light minutes is nothing in cosmic terms. The nearest star beyond the sun, Proxima Centauri, is 4.24 light-years away. Its light takes 4 years and 3 months to reach us. When you look at Proxima Centauri on a clear night, you are seeing it as it was 4 years ago, before events that have since occurred, before changes that have since happened, before whatever is happening there right now that will not reach your eyes for another 4 years. The star you see is a historical artifact. The star as it currently exists is invisible to you and will remain so for years. The star Sirius, the brightest star in the night sky, is 8.6 light-years away. You see it as it was during a specific year in the recent past. Betelgeuse, the bright reddish star in Orion's shoulder, is approximately 700 light-years away. You see it as it was 700 years ago. Right now, tonight, Betelgeuse might already have exploded. It might be in the middle of exploding. It is already known to be near the end of its stellar life, a red supergiant expected to detonate as a supernova within the next 100,000 years or so, which, in astronomical terms, is imminent. If it exploded yesterday, you will not know for 700 years. If it exploded 600 years ago, the light from the explosion is already on its way and will arrive within the next century. You will not see the supernova when it happens. You will see it 700 years after it happens. The Andromeda Galaxy, the nearest large galaxy to our own, is 2.537 million light-years away. The light reaching your eyes from Andromeda tonight left its source when your species did not yet exist. Homo sapiens emerged roughly 300,000 years ago. The photons arriving from Andromeda tonight have been traveling for more than 8 times the entire span of human existence. When that light departed, there were no human eyes to receive it, no nervous systems to interpret it, no minds to wonder at it. And yet here it is, completing its journey, arriving at a pair of eyes that evolved specifically to make use of it, on a planet that did not yet have the biology to produce those eyes when the light was launched. What you see when you look at the night sky is not the universe as it currently exists. It is a composite photograph of the universe at many different moments in the past, each source at a different temporal distance, each star and galaxy a different aged snapshot overlaid on the same patch of darkness. The night sky is a time machine pointing backward. Every direction you look is a different depth into cosmic history, and this leads directly to the question that should already be forming. If we can see only the past, how much of the past can we see? Is there a limit? Can we, in principle, look back far enough to see the Big Bang itself? And if so, what would we find there? And what does it mean for our understanding of what the universe is and where it came from? The answer involves one of the most important objects in cosmology, something called the cosmic horizon, and understanding it requires understanding what it means for the universe to have a finite age in a way that most descriptions never fully convey. Before we get there, let us sit with the speed of light for a moment, because its consequences go far deeper than the delay in seeing stars. The finite speed of light is not a fact about light specifically. It is a fact about the structure of space-time. Einstein's special theory of relativity, published in 1905, is fundamentally a theory about the speed of light. Its 2 core postulates are that the laws of physics are identical in all inertial reference frames, and that the speed of light in a vacuum is the same for all observers regardless of their motion. From these 2 simple postulates, Einstein derived consequences that demolished 3 centuries of assumptions about the nature of space and time. The derivation that matters most for our purposes is the one that leads to the universal speed limit, because light travels at the same speed for all observers, and because simultaneity, what counts as happening at the same moment, turns out to be observer-dependent rather than absolute, and because causality requires that causes precede their effects in every reference frame, the mathematics demands that nothing carrying information can travel faster than light. This is not a statement about the current limitations of rocket engines. It is not a statement about engineering challenges awaiting future technology. It is a statement about the causal structure of the universe. A universe in which information could travel faster than light is a universe in which effects could precede their causes. It is a universe in which the concept of causality, the most fundamental organizing principle of physical law, breaks down. The speed of light is the speed of causality. It is the maximum rate at which any influence can propagate through space. This has an immediate consequence for how much of the universe can ever be relevant to us. Every event that has ever affected us, every cause that has produced any effect on Earth, every piece of information that has ever reached us, must have originated within what physicists call our past light cone. The cone of space-time from which signals traveling at the speed of light could have reached our location by now. Events outside the past light cone are not just distant, they are causally disconnected from us. Nothing that has ever happened outside our past light cone has ever affected anything that has happened on Earth. Nothing ever can, by definition. The past light cone is not just our field of view. It is the totality of physical reality that has any bearing on our history. The history of how physicists came to understand this deeply is worth tracing because it is a story of successive conceptual revolutions, each one expanding the apparent size of the universe, and each one simultaneously revealing a new kind of limitation on what we can ever know about it. For most of human history, the question of how far you could see was purely a practical question about instrument capability. Better telescopes meant seeing farther. There was no obvious reason in principle why there should be a horizon, a limit beyond which not just our instruments, but the universe's causal structure prevented any signal from reaching us. The universe was assumed to be infinite and static, eternal in both directions of time, with matter spread through it uniformly and no particular origin or edge. In this picture, the question of what we can see is purely a question of the sensitivity of our detectors. That picture began to change in the early 20th century. In 1917, Einstein applied his newly completed general theory of relativity to the universe as a whole, and found, to his consternation, that his equations predicted a universe that was either expanding or contracting. A static universe was not a solution to his equations unless he introduced an artificial term, which he called the cosmological constant, specifically to hold the universe still. He inserted it, later describing this as the greatest blunder of his life, because the equations without it were telling him something he was not ready to believe. In the 1920s, the astronomer Edwin Hubble, working at the Mount Wilson Observatory in California with what was then the world's most powerful telescope, measured the distances to spiral nebulae, the fuzzy patches of light scattered across the sky that had been debated for decades. Were they clouds within the Milky Way or separate island universes at enormous distances? Hubble settled the debate using Cepheid variable stars, which pulsate with periods directly related to their intrinsic brightness, allowing distances to be calculated by comparing apparent brightness to intrinsic brightness. The spirals were not local. They were enormously distant, separate galaxies each containing hundreds of billions of stars. The universe was incomparably larger than anyone had imagined. But Hubble found something else. He measured the spectra of these distant galaxies and found that almost all of them were redshifted. Their light shifted toward longer wavelengths in a way consistent with the galaxies receding from us. And the recession velocity was proportional to distance. Twice as far meant twice as fast. This relationship, now called Hubble's law, had only one coherent interpretation. The universe was expanding. Every galaxy was moving away from every other galaxy as the space between them stretched. Rewinding the expansion backward in time implied that the universe had once been far smaller, far denser, far hotter, and that it had a definite beginning. The Belgian priest and physicist Georges Lemaitre had actually predicted this result, theoretically in 1927, deriving the expansion from Einstein's equations and estimating the rate. He called the initial state the primeval atom. The name that stuck came later, introduced ironically by the astronomer Fred Hoyle in a 1949 radio broadcast as a dismissive label for what he considered a scientifically dubious idea. He called it the Big Bang. The name stuck even though Hoyle's skepticism did not. The confirmation that the universe had a beginning was the first step toward understanding why there is a cosmic horizon. If the universe began at a specific moment in the past, then the maximum distance any signal can have traveled since the beginning is the distance light could have traveled in the universe's entire lifetime. Even in an infinite universe, only the portion within this maximum distance is causally connected to us. Beyond it, events are occurring right now. Structures exist right now, but nothing that is happening there has had any effect on us, and nothing we do will affect them for longer than the universe has currently existed. We are surrounded by an observational horizon determined not by the edge of the universe, but by the finite age of the universe combined with the finite speed of light. The universe is approximately 13.8 billion years old. You might therefore expect the cosmic horizon to sit at a distance of 13.8 billion light-years. Any signal traveling at the speed of light for 13.8 billion years covers 13.8 billion light-years. Everything within that distance is in our past light cone. Everything outside it is not. But here is where the expanding universe complicates the picture in a way that is genuinely surprising. When light was emitted by distant objects early in the universe's history and began traveling toward us, the universe was much smaller and the source was much closer. But while the light was traveling, space was expanding, carrying the source farther away. The photon kept traveling toward us at the speed of light relative to local space, but the destination was moving away as the source moved away. The light still arrived eventually, but the source that emitted it is now much farther away than the distance the light traveled. The observable universe, the region from which light has had time to reach us since the Big Bang, has a radius not of 13.8 billion light-years, but of approximately 46.5 billion light-years. Sources at the edge of the observable universe, sources whose ancient light is just now arriving at our telescopes, are now located 46.5 billion light-years away, even though the light that is just reaching us left them when they were only about 42 million light-years away. In the early universe, when everything was compressed into a much smaller volume. The observable universe is a sphere 93 billion light-years in diameter, centered on Earth. This centering on Earth is not a statement about Earth's special cosmic position. Every observer in the universe is at the center of their own observable sphere. An observer in a galaxy 10 billion light-years away has a different observable sphere than ours, with a different 46.5 billion light-year radius centered on their location. These spheres overlap but are not identical. They see different slices of the universe's past. The oldest light in our observable universe is the cosmic microwave background, the thermal radiation that filled the early cosmos. It was produced approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely for the first time. Before that moment, the universe was an opaque plasma. Photons were continuously absorbed and re-emitted, unable to travel any significant distance before interacting with a charged particle. The universe was bright everywhere and opaque everywhere simultaneously. Then, in a transition called recombination, the charged particle sea condensed into neutral atoms. The opacity dropped dramatically, and the photons that had been trapped in the plasma were suddenly free. They have been traveling ever since. Those photons are what we detect as the cosmic microwave background. They are not coming from a specific direction. They are coming from every direction simultaneously, because the surface of last scattering, the spherical shell at the boundary of the opaque early universe from which these photons were last scattered before traveling freely, surrounds us on all sides. We are inside a sphere of ancient light. Every direction we point a sensitive microwave detector shows us the same faint glow at a temperature of 2.725 Kelvin, the thermal energy of the early universe, cooled by 13.8 billion years of cosmic expansion from the roughly 3,000 Kelvin it had when it was released. The discovery of the cosmic microwave background is one of the most remarkable in the history of science, and it is worth telling because the circumstances of the discovery illuminate something important about the relationship between theoretical prediction and experimental confirmation. In the late 1940s, the physicists George Gamow, Ralph Alpher, and Robert Herman worked out the physics of what the first minutes of the universe should have looked like if it had begun in a hot, dense state. They predicted that the primordial universe would have been so hot that nuclear reactions would have occurred, fusing some of the initial hydrogen into helium and trace amounts of heavier elements in a process now called Big Bang nucleosynthesis. They also predicted that the radiation field of the early universe, stretched and cooled by expansion, should still permeate all of space, detectable as a uniform thermal glow at a temperature of roughly a few Kelvin. This prediction sat largely unnoticed for 15 years. The microwave detectors of the late 1940s were not sensitive enough to detect the predicted signal, and few astronomers were looking for it. Then, in 1964, at the Bell Telephone Laboratories in Holmdel, New Jersey, the radio astronomers Arno Penzias and Robert Wilson were attempting to use a large horn antenna, originally built for satellite communications, for radio astronomy. They found an annoying and persistent excess noise in their instrument, a uniform hiss coming from every direction in the sky, which they could not eliminate or explain. They tried everything, including famously cleaning out pigeon droppings from inside the horn, suspecting that biological contamination might be affecting the receiver. The noise persisted, equal in every direction, unchanged through the seasons as Earth orbited the Sun, constant through the night as the galaxy rotated overhead. Meanwhile, at Princeton University, a few miles away, a team led by Robert Dick was building a detector specifically designed to find the cosmic microwave background, having independently worked out the prediction. When Penzias and Wilson contacted the Princeton group, it took very little time to realize that what the Bell Labs antenna had been detecting for months was exactly what the Princeton team was building a detector to find. Penzias and Wilson had discovered the cosmic microwave background by accident, while trying to get rid of a noise they thought was a problem. They received the Nobel Prize in Physics in 1978. Dickey, who had done much of the theoretical groundwork, did not receive a share of the prize. The cosmic microwave background is now one of the most precisely characterized phenomena in all of science. The satellite observatories COBE, WMAP, and Planck have mapped it with extraordinary precision, measuring temperature variations across the sky at the level of 1 part in 100,000. Those tiny temperature variations, the seeds of all cosmic structure, reveal information about the early universe that is otherwise inaccessible. They encode the density variations in the plasma of the early universe that gravity subsequently amplified into the galaxies and galaxy clusters we see today. The pattern of these variations, their statistical properties, their angular scale, tells us about the composition of the universe, its geometry, its age, and the nature of the initial conditions that produced it, with a precision that no other observational tool can match. Looking at the cosmic microwave background is looking back to the surface of last scattering, 380,000 years after the Big Bang. We cannot see further back using electromagnetic radiation because the universe before that moment was opaque to it. We can use other messengers, neutrinos, which interact so weakly with matter that they would have streamed freely through the early plasma, decoupled from the rest of the universe about 1 second after the Big Bang. A cosmic neutrino background analogous to the cosmic microwave background should exist, carrying information about conditions in the universe at 1 second of age. Current technology cannot detect it. The neutrinos from the early universe have been redshifted to such low energies that detecting them requires detectors of a sensitivity not yet achieved. Gravitational waves, ripples in space-time itself, travel at the speed of light and interact with matter even more weakly than neutrinos. A background of primordial gravitational waves produced in the first fraction of a second of the universe's existence, perhaps by quantum fluctuations during an epoch of rapid inflation, could in principle provide a window into moments far earlier than the surface of last scattering. Detecting this background is a goal of the next generation of gravitational wave observatories, including space-based detectors planned for the coming decades. If detected and interpreted correctly, primordial gravitational waves would tell us about the universe at energies and temperatures and times that electromagnetic observation can never reach. But there is a limit even to this. Before approximately 10 to the negative 43 seconds after the Big Bang, the Planck epoch, the density and temperature of the universe were so extreme that quantum gravitational effects dominated. We do not have a working theory of quantum gravity. General relativity, which describes gravity beautifully at large scales, breaks down when space-time curvature approaches the Planck scale. Quantum mechanics, which describes the behavior of particles at small scales, does not include gravity in a consistent way. A complete theory that unifies the two, sometimes called quantum gravity or a theory of everything, does not yet exist in a confirmed form. The Planck epoch is therefore not just observationally inaccessible, it is theoretically inaccessible. We cannot say what happened then because the physics we have is not adequate to describe it. The cosmic horizon, as we usually describe it, the surface of last scattering, the boundary of the observable universe at 46.5 billion light-years, is therefore not the deepest possible limit, but the practical electromagnetic limit. Beyond it, in the theoretical sense, lie the neutrino background, the gravitational wave background, and eventually the Planck wall, beyond which current physics simply has nothing to say. Now, the universe is not just expanding, it is accelerating. This fact, discovered in 1998 by two independent teams of astronomers measuring the brightnesses of distant Type 1a supernova and finding that they were dimmer than expected for their recession velocities, implying they were farther away than a uniformly decelerating universe would place them, is one of the most consequential discoveries in the history of cosmology. The two teams, led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, had set out expecting to measure the rate at which the expansion was slowing down under gravity, what is called the deceleration parameter. Instead, they found that the expansion was speeding up. The universe's expansion rate is not decreasing, it is increasing. The galaxies are not just moving apart. They are moving apart faster and faster with every passing moment. This acceleration implies the existence of something pervading all of space and exerting a repulsive gravitational effect. Something given the name dark energy. Something whose nature is almost entirely unknown. Something that constitutes approximately 68% of the total energy content of the universe. The implications of accelerating expansion for the cosmic horizon are severe and have not been fully absorbed into popular understanding. In a universe that was expanding at a constant rate or decelerating under gravity, the horizon would be growing. Light from regions currently just beyond our horizon would eventually reach us as the horizon expanded outward. The observable universe would grow over time as new regions came into causal contact with us. But in an accelerating universe, the opposite happens. The expansion is speeding up. The recession velocities of distant galaxies are increasing. There is a distance, the Hubble sphere, beyond which galaxies are receding faster than the speed of light relative to us. This is not a violation of special relativity. The galaxies are not moving through space faster than light. The space between us and them is expanding, and the total expansion velocity, which is not a velocity through space but a rate of spatial expansion, can exceed the speed of light without violating any physical law. But the consequence is that light emitted right now by a galaxy beyond the Hubble sphere cannot reach us. The galaxy is receding faster than the light can travel toward us. The light is making progress through local space toward us, but the space between us and the source is expanding faster than the light can cross. The light will never arrive. The event horizon, the boundary beyond which events happening right now cannot ever send a signal that reaches us, sits at approximately 16 billion light years. Anything currently farther than 16 billion light years from us is beyond our event horizon. We can see it because ancient light from before it crossed the horizon is still reaching us. But anything that happens there from this moment onward is lost to us forever. No signal, no influence, no information from those events will ever reach us. And because the expansion is accelerating, the event horizon is shrinking in co-moving coordinates over time. More and more of the universe is crossing beyond our event horizon. Galaxies we can currently exchange signals with will eventually recede beyond our ability to reach them. The fraction of the universe with which we can have any causal connection is getting smaller, not larger. In the very distant future, if the acceleration continues and dark energy maintains its current character, essentially all the galaxies we can currently see will have receded beyond the event horizon. Only the galaxies in our local group, gravitationally bound to us and therefore not participating in the general cosmic expansion, will remain within causal reach. Observers in that distant future will look out at an apparently empty universe, with nothing beyond their own galaxy to observe, and may have no way of knowing that a vast cosmic structure of billions of galaxies once existed within their ancestral horizon. This is a profound observational point that deserves more attention than it usually receives. We happen to live at a cosmologically fortunate moment, an era when the observable universe still contains a rich sample of the cosmos, when the effects of cosmic structure formation are visible across billions of light years, when the evidence for the Big Bang's history is still legible in the light of distant galaxies and in the texture of the microwave background. In 100 billion years, much of this evidence will have receded beyond the horizon. The cosmic microwave background will have redshifted to such low energies it will be undetectable. The distant galaxies will be gone. An observer then will have far less to work with. We are living in a window of cosmic observability. That window is open now. It will not remain open indefinitely. Let us now talk about what lies beyond the observable universe, because this is where the physics becomes genuinely difficult to discuss honestly. The observable universe, the 46.5 billion light-year sphere centered on our location, is not the whole universe. It is the portion of the universe from which light has had time to reach us. The universe beyond our horizon is not some hypothetical or speculative region. It is as real as the region we can see. Matter exists there. Galaxies are forming there. Stars are burning there. Events are occurring there. None of this is reaching us because the light has not had time to arrive, and in the accelerating universe, much of it never will. How large is the universe beyond our horizon? Honest answer is, we do not know. It is at minimum very large. The simplest cosmological models consistent with our observations, particularly the observed near-perfect flatness of the universe's spatial geometry, as measured by the pattern of the cosmic microwave background, predict that the total universe is vastly larger than the observable portion. Some models predict it is infinite. An infinite universe would mean that the observable portion, however large it seems, is an infinitely small fraction of the whole. If the universe is infinite, and if the laws of physics and the initial conditions that produced our part of it are the same elsewhere, which follows if the universe is uniform at large scales, as the cosmological principle asserts, then the same structures that exist within our observable volume exist elsewhere in infinite repetition. Every galaxy cluster configuration, every star arrangement, every planetary system, every biological accident that produced any observer anywhere has occurred infinitely many times elsewhere, in an infinite universe. This is not mysticism. It is combinatorics applied to an infinite volume. An infinite universe with a finite number of possible states per unit volume contains every possible state an infinite number of times. This is a deeply strange conclusion that most physicists accept as a logical consequence of standard cosmology, while recognizing that it is unverifiable in principle. We cannot see beyond our horizon. We cannot confirm what exists there. The extrapolation from the observable to the unobservable is not science in the usual sense of making predictions that can be tested. It is a logical inference from the physics we observe applied to conditions we cannot observe. Whether that constitutes a scientific claim or a philosophical one is a matter of active debate. The inflationary universe, the leading framework for explaining the initial conditions of the Big Bang, pushes this extrapolation much further and in a more radical direction. Inflation is a proposal that in the first fraction of a second of the universe's existence, a period of extraordinarily rapid exponential expansion occurred, driven by the potential energy of a scalar field called the inflaton. During this period, a region of space far smaller than a proton expanded to a size larger than our current observable universe, in an interval so brief that ordinary clocks cannot meaningfully describe it. Inflation was proposed in 1980 by the physicist Alan Guth to explain several features of the observable universe that standard Big Bang cosmology could not account for. Why is the universe so spatially flat when a randomly chosen initial condition might be expected to produce significant curvature? Why is the cosmic microwave background so uniform in temperature in every direction, even in regions of the early universe, that should not have been in causal contact and therefore could not have exchanged energy to reach thermal equilibrium? And why are there no magnetic monopoles or other exotic relics that grand unified theories of particle physics predict should have been produced in the hot early universe? Inflation solves all three problems simultaneously. The exponential expansion flattens any initial curvature, just as inflating a balloon makes its surface locally flat no matter how wrinkled it started. It takes a tiny, causally connected region and expands it to cosmic scales, explaining the uniformity of the microwave background across regions that were never in causal contact after inflation, but were thoroughly mixed before it. And it dilutes the density of any exotic relics to negligible levels. The predictions of inflation are in excellent agreement with observations. The specific pattern of temperature fluctuations in the cosmic microwave background, their statistical distribution and power spectrum match the predictions of simple inflationary models with remarkable precision. The confirmation of this agreement by WMAP and Planck is considered strong indirect evidence for inflation, though not proof. A specific prediction of inflation that has not yet been confirmed is the existence of primordial gravitational waves, tensor perturbations in space-time, produced during the inflationary epoch. Their detection would constitute powerful evidence for inflation. Their non-detection at current experimental sensitivity is constraining but not conclusive. But inflation also predicts something that goes far beyond explaining the observable universe. In most inflationary models, inflation does not simply end everywhere simultaneously. Quantum fluctuations in the inflaton field cause inflation to end at different times in different regions of space. In regions where fluctuations happen to sustain the inflationary condition a bit longer, inflation continues while neighboring regions have already ended their inflationary phase and evolved into universes like ours. This process, called eternal inflation, produces an endlessly branching structure of separate regions, each potentially with different properties, each causally disconnected from the others. This is the multiverse, a term that encompasses many distinct theoretical concepts, but that in the eternal inflation context refers to a potentially infinite collection of regions, each evolving as a separate universe, each inaccessible to the others. If eternal inflation is correct, our observable universe is one bubble in an incomprehensibly vast structure of other bubbles, each the product of a local end to inflation, each potentially with its own physical constants and particle content, each expanding and evolving in isolation. The light cone of any observer in any bubble never reaches another bubble. The separation is not a distance in the usual sense. It is a causal disconnection enforced by the inflationary expansion that continues between bubbles. Nothing we can ever observe from within our universe can directly confirm the existence of other bubbles. The multiverse, in this sense, may be observationally indistinguishable from the simpler possibility of a single finite universe. This places inflation in an uncomfortable scientific position. The framework itself is supported by the pattern of the microwave background fluctuations and the flatness and uniformity of the observable universe. These are real predictions, testable and tested. But the multiverse prediction is a logical consequence of the framework that is not separately testable. If you accept eternal inflation on the basis of its testable predictions, you are also committed to the multiverse as a logical implication, regardless of whether the multiverse can itself be tested. This has driven a genuine and unresolved debate about whether the multiverse is science or philosophy. Let us now talk about what it means to be on the edge of the observable universe, because the concept of the cosmic horizon is not just a distant abstraction. It has direct consequences for what we can know, how we should reason about the cosmos, and what the ultimate limits of scientific knowledge are. Every measurement we make of the cosmos is a measurement of a sample. The observable universe is a sample of whatever the total universe is. The question of whether our sample is representative is a genuine scientific question, with potentially testable consequences. The cosmological principle, the assumption that the universe is homogeneous and isotropic at large scales, is the assumption that our sample is representative. It says that the observable universe is not special, not a particularly dense or sparse or structured region that would give a misleading picture of the whole. It is an assumption supported by the uniformity of the microwave background and the statistical homogeneity of the galaxy distribution at large scales, but it is not proven. It is an extrapolation from what we can see to what we cannot see, a universe that becomes strongly non-uniform beyond our horizon would violate the cosmological principle while being consistent with all our observations. There are hints in the data of possible violations. Large-scale anomalies in the cosmic microwave background, including a slight asymmetry in power between opposite hemispheres of the sky and a cold spot in the direction of the constellation Eridanus, have attracted attention as possible evidence that the universe is not perfectly homogeneous on the largest scales. These anomalies have been detected in both WMAP and Planck data. Their statistical significance is debated. They may be genuine physical features. They may be statistical fluctuations in a random field that will occur occasionally even in a perfectly homogeneous universe. The cold spot has a candidate physical explanation in a large void, a region of lower than average galaxy density, along the line of sight that might produce the observed temperature decrement through an effect called the integrated Sachs-Wolf effect. Whether this explanation is sufficient is still being investigated. There is another claimed anomaly that is more difficult to explain. In 2020, an analysis of radio galaxy surveys found that the dipole, the slight asymmetry in the distribution of galaxies across the sky that should match the dipole in the cosmic microwave background caused by our motion through the universe, did not match. The radio galaxy dipole was larger than expected and pointed in a slightly different direction. If confirmed, this would suggest that either the radio galaxy surveys have systematic errors, which is the most conservative explanation, or that the universe has a larger scale structure that makes our local observable volume non-representative. The statistical significance of this anomaly has grown with subsequent analyses, and it remains an active area of investigation. These observations are not established violations of the cosmological principle. They are anomalies that may be explained within the standard framework with more data, or may persist and demand new explanations. But they illustrate the genuine scientific question: is our observable sample of the universe representative? We cannot answer this without looking beyond our horizon. We cannot look beyond our horizon. This is the fundamental epistemic situation of cosmology. Now, let us talk about time, because everything we have been discussing about spatial horizons has a temporal dimension that is equally profound and equally strange. The light cone structure of space-time means that there is a future light cone, as well as a past light cone. The past light cone encloses everything that could have affected us. The future light cone encloses everything we can affect. And the observable universe, bounded by the past light cone, is bounded in time as well as space. Looking at the cosmic microwave background, as we established, is looking back to 380,000 years after the Big Bang. Looking at the most distant galaxies is looking back approximately 13 billion years, to a time when the universe was less than 1 billion years old, and galaxies were young and violently star-forming. Every telescope is a time machine. We literally see the past because we are receiving information that traveled to us through space and whose travel time is non-negligible. This means that our picture of the current state of the universe is assembled from snapshots taken at different times. When we look at nearby galaxies, we see them roughly as they are now. When we look at galaxies 1 billion light-years away, we see them as they were 1 billion years ago. When we look at the cosmic microwave background, we see the universe as it was 13.4 billion years ago. We have no way of seeing what any of these things look like right now. We have no way of knowing whether the galaxy we see 1 billion light-years away is still a galaxy, or has merged with a neighbor, or been disrupted. We see only the message that left 1 billion years ago, not the source as it currently exists. This temporal dimension of the horizon is also affected by the accelerating expansion. The future light cone, the region of the universe that we can influence with signals sent right now, is bounded by the event horizon. Signals we send today will reach destinations up to approximately 16 billion light-years away. They will not reach destinations beyond that. As the universe continues to accelerate, the event horizon continues to shrink in co-moving coordinates. Our ability to influence the universe around us is diminishing over time, not growing. In the far future, we will be causally isolated in our local group, unable to send or receive signals from the wider universe, unable to affect or be affected by anything beyond our gravitational neighborhood. There is something philosophically significant about this situation that most accounts of cosmology do not address head-on. We live in a universe where the observable portion is shrinking, where the evidence for cosmic history is being erased by the recession of its sources beyond the horizon, where our ability to influence the universe is contracting rather than expanding. We are not at the dawn of an era of ever-increasing cosmic access. We are possibly at or near its peak, living in the window of maximum cosmic observability before the accelerating expansion seals us into an ever smaller, causally connected region. This has implications for the project of cosmology itself. Every piece of evidence we collect about the large-scale universe is evidence that future observers will not have. The light from distant galaxies that is reaching us now, carrying information about the early universe, will have receded beyond the horizon before observers in the far future can collect it. The cosmic microwave background, red-shifted to negligible energies, will become undetectable. The evidence for inflation, for the Big Bang, for the large-scale structure of the universe may all be lost to future observers who will have only the local group to observe. If they do cosmology at all, they may arrive at a picture of a static, finite, island universe with no evidence of the vast structure surrounding it. This is an argument for urgency in the present program of observational cosmology. Every measurement we make of the large-scale universe is a measurement that cannot be remade by future observers. We are not building toward a future of ever-increasing completeness. We may be living in the era of maximum available information. The science of cosmology is in a race with the recession of its sources. Let us now talk about the light from the most distant objects ever observed, because the practical details of what we can actually see illuminate the abstract geometry of the cosmic horizon in concrete and specific ways. The most distant individual objects observed as of the current frontier of observations are galaxies seen in deep field images by the Hubble and James Webb Space Telescopes. The James Webb Space Telescope, launched in December 2021 and operational from mid-2022, has extended the observational frontier to redshifts above 13, corresponding to light travel times of more than 13.4 billion years. These are galaxies seen as they existed when the universe was less than 400 million years old, when the first stars were forming and ionizing the neutral hydrogen that had filled the universe since recombination. What do these early galaxies look like? They are small, often compact, frequently irregular in morphology compared to the elegant spirals and ellipticals of the current universe. They are vigorously forming stars at rates far higher per unit mass than typical galaxies today. Some of them are surprisingly massive for their age, challenging our models of how quickly galaxies can assemble their stars in the early universe. The James Webb Space Telescope has found early galaxies that appear to have formed a surprisingly large fraction of their eventual stellar mass before the universe was even 500 million years old, a pace of galaxy formation that some standard models did not predict, and that is driving ongoing revisions of our understanding of early cosmic history. The detection of these galaxies is itself a triumph of engineering and astrophysics combined. The James Webb Space Telescope observes primarily in infrared wavelengths because the light from the most distant galaxies, originally emitted in ultraviolet and visible wavelengths, has been redshifted to infrared by the expansion of the universe. A galaxy at redshift 10 has had its light wavelengths stretched by a factor of 11, shifting ultraviolet photons into the near-infrared where Webb's instruments are most sensitive. The telescope must operate at temperatures near absolute zero, cooled to approximately 40 Kelvin for most of its instruments, and even colder for its mid-infrared detector, to prevent its own thermal emission from overwhelming the faint signals from distant galaxies. The telescope is located at a gravitationally stable point, called the second Lagrange point, 1.5 million kilometers from Earth, in the direction away from the Sun, where it can maintain a stable thermal environment shielded from solar radiation by a sunshield the size of a tennis court. This location allows the telescope to see in directions that are impossible from Earth's surface or from low Earth orbit, and to cool to temperatures required for infrared sensitivity without the complication of Earth's thermal radiation flooding the detectors. Every photon that Webb detects from a galaxy at redshift 13 has been traveling for 13.4 billion years. It was emitted by a young star in an infant galaxy when the universe was perhaps 2% of its current age, before the Milky Way had fully assembled, before the solar system existed, before the Earth existed, before any complex chemistry had had time to operate anywhere in the observable universe. That photon traveled for over 13 billion years through an expanding universe, through intervening structures of gas and dark matter, to fall finally on a detector cooled to 40 Kelvin in a spacecraft 1.5 million kilometers from Earth, and be recorded as a data point in a spectrum being analyzed by astronomers who want to know what the universe was doing in its first few 100 million years. This chain of physical processes, from photon emission in an infant galaxy to detection in a modern observatory, is one of the most extraordinary things that humans have organized themselves to accomplish. It is worth appreciating not just for its scientific content, but for what it says about the relationship between the cosmic horizon and the information we can wring from the photons that breach it. The photons from the earliest galaxies carry direct information about the state of the universe at the time of their emission. But they carry that information with losses. The intergalactic medium absorbs certain wavelengths. Gravitational lensing by intervening structures magnifies some objects and distorts others. The expansion of the universe stretches wavelengths in a way that can be corrected for, but adds uncertainty. Recovering a clean picture of the early universe from ancient redshifted distorted photons requires sophisticated astrophysics applied at every step of the process. The faintest and most distant objects at the edge of the observable universe are not clearly resolvable. They appear as smudges of a few pixels in deep field images, their morphology blurred by their distance and the resolution limits of the instruments. We are seeing them barely. We are extracting information from signals so faint that they represent only a few photons per second arriving at the detector. At this frontier, the observable universe and the limits of our instruments coincide. We are pushing against both simultaneously. Now, let us talk about what we cannot see. Not just what is beyond the observable horizon, but what is there in principle to see, and whether the light from it will ever reach us. The surface of last scattering at redshift. 1,100 is the farthest we can see using electromagnetic radiation. Beyond it, the universe was opaque. But the matter that existed beyond it was not itself beyond our horizon. The matter that produced the cosmic microwave background was ordinary matter following the same physics as matter everywhere. It has since evolved. The gas clouds that last scattered the background photons we now detect have since collapsed into galaxies. Those galaxies have evolved over 13.8 billion years, and those evolved galaxies now exist at distances far greater than 46.5 billion light-years, because the universe has expanded since the scattering epoch. There are galaxies in the universe whose oldest light, the light emitted at the moment of last scattering, is only just reaching us now as the cosmic microwave background. Those same galaxies have since evolved into their current form, which exists at enormous distances from us right now, distances far outside our event horizon. The evolved form of the matter that produced the microwave photons reaching us is beyond our reach forever. We see the infant version as a component of the microwave background. The adult version is beyond the event horizon and will never be seen. This is the deepest version of the temporal horizon problem. It is not just that we see the past. It is that we see the deep past of objects that have since evolved into forms that are causally disconnected from us. The universe we observe is younger than the universe that currently exists everywhere. The universe, as it currently exists everywhere, cannot be observed. We are always and irreducibly seeing history. What does it feel like, standing in this situation? What should it feel like to know that the sky above you is a composite image of the universe at many different moments in the past? That the nearest stars are years old in their light, and the farthest galaxies are billions of years old in theirs? That the faint, uniform glow of the microwave background comes from a universe that existed 13.4 billion years ago, and that the matter producing it has since evolved beyond our sight, beyond our reach, beyond any possibility of communication forever. Go outside on a clear night. Look up. Every point of light in the sky is a message from the past. The moon's light is a little over a second old. The light from Jupiter is at minimum 33 minutes old, depending on orbital positions. The light from Sirius is 8.6 years old. The light from the Andromeda Galaxy is 2.5 million years old. The light from the most distant galaxies Webb can see is over 13 billion years old. You are not looking at the universe. You are looking at the universe's autobiography, written in light, with earlier chapters visible at greater distances, and the most ancient chapters barely legible at the edge of the observable sphere. The universe is not what you see when you look up. What you see when you look up is what the universe was. What the universe is right now, at this moment, across its full extent, is invisible to you and always will be. The observable portion is a bubble of ancient light centered on your location. Beyond the bubble, the universe continues, unobservable, affected by physics identical to what you can see, but inaccessible to any signal you could send or receive. And within the bubble, even the most sophisticated instruments probe only what was, not what is. Every photon is a fossil. Every spectrum is a historical document. Every deep field image is an archaeology of cosmic time. This should not be a source of despair. It is a source of wonder. That we have gotten this far, that we have assembled this much of the universe's history from fossils and documents and archaeologies of light, that we have traced the story from the present moment back to 380,000 years after the universe began, and in some ways back to the first second, that we are now pushing deeper with tools like the James Webb Space Telescope and reaching the edge of what electromagnetic observation can achieve, is one of the extraordinary accomplishments of the species. The limits are real and are not going to be overcome. The speed of light cannot be exceeded. The age of the universe cannot be extended. The cosmic horizon cannot be moved. These are not engineering problems. They are features of physical reality that define what it means to be an observer embedded in a causal spacetime. Every observer in the universe, wherever they are, is surrounded by their own horizon, their own bubble of observable history, their own cut through the cosmic autobiography. Ours happens to be the one from which we do our physics. The universe is 13.8 billion years old. Its observable portion extends 46.5 billion light-years in every direction. Beyond that horizon lies a universe we cannot see, that may extend infinitely, that contains the evolved forms of the matter we observe as the ancient microwave background and the early galaxies, that is causally disconnected from us and from which we will never receive information. Our event horizon is at approximately 16 billion light-years and contracting as the expansion accelerates. Our cosmic window is open right now and will narrow over cosmic time. We are in the light cone. We are in the observable sphere. We are receiving photons that have been traveling toward us for billions of years, arriving from the edges of what physics allows us to access, carrying information about a universe younger than the one that currently exists. And we are looking at them with instruments we built, interpreting them with theories we derived, assembling a picture of a cosmos whose full reality we can never see. The light entering your eyes right now is 8 minutes old. It left the sun before you were reading this, before you knew these particular photons existed, before they had crossed the void and found their way to you. That delay is not a flaw. It is the nature of a universe in which light travels at a finite speed, in which information cannot move faster than causality allows. in which every observer is surrounded by a bubble of accessible history and nothing beyond it. You are inside the bubble. Everything you will ever see is inside the bubble. The universe is much larger than the bubble. And right now, in this moment, photons that left the surfaces of galaxies at the edge of your observable sphere 13 billion years ago are completing their journey, arriving at the detectors of orbiting telescopes, being collected and analyzed and turned into images of infant structures at the dawn of cosmic time. They made it, just barely, just in time, before the accelerating expansion would have carried their sources beyond any possibility of communication. Those photons crossed 46 billion light-years to deliver a 13 billion-year-old message about what the universe was doing at the beginning. And we received it. That is what cosmology is. That is what the cosmic horizon means in practice. Not a wall, not an edge, but a boundary of accessible history. A limit on what any observer anywhere can know about the cosmos they inhabit. A fundamental constraint written into space-time by the finite speed of causality and the finite age of everything. We observe from within it. We reason carefully about what lies beyond. And the light keeps coming older and older at greater and greater distances until at the surface of last scattering, it stops being information we can receive through electromagnetic means and becomes a background glow, the oldest light in the universe, arriving equally from every direction, telling us about a moment when the universe was 380,000 years old, and everything that came before that moment remains, for now, beyond the reach of any signal we know how to detect. That is where we stand. That is the horizon. You have been watching the entire history of the universe. Do not forget to like and subscribe, and leave a comment to tell us what you think. Thanks for watching, and we will see you next time.